Hello students, this is my video on quantum numbers. So we've seen a little bit about this topic before when we talked about hydrogen emission and absorption of energy. So we've looked at this energy scale for the different energies an electron can have. It can absorb energy and go up to a higher energy level, then go down in energy and emit that energy as a photon. And we called these energy levels just n equals 1, n equals 2, and so on down the line, with 6 being the highest possible for the hydrogen electron. So these energy levels are actually the different quantum numbers that are possible for excited hydrogen atoms. What we're going to talk about are quantum numbers, and those are for ground state atoms, and ground state electrons. And also, I'll only be talking about uncharged atoms. Okay, so for quantum numbers, I'm going to be talking about the periodic table a bit, and there are some different names I want you guys to be familiar with. So there are some different areas of the periodic table, and here on the right and left side, these two kind of higher areas, everything that I've outlined in these black boxes is called the main group elements. Then here in the center, this area that's a little bit lower, this area is called the transition metals. Then we have these two rows down below. So you can see by the symbols that they come from these other rows up top, but these extra elements are put down below to make the periodic table look nice on a page. And so this whole area here is called the inner transition metals. So I'll be using these terms in the video today. Okay, so there are 4 different types of quantum numbers we're going to talk about today. And the first one is called the principal quantum number n, which you saw with the hydrogen atom. So first of all, let's talk about the main group elements. For those elements, whatever their rho is also the value of their principal quantum number. So n equals 1, that would be for hydrogen and helium here in this top row of the periodic table. We have n equals 2 for all the elements here in the second row, and then so on. And throughout the video, you'll probably want to have your periodic table with you and maybe making notes on that as well. So those are the main group elements where their rho is their principal quantum number. Now we have the transition metals, and these elements are a little different. You can see that they are also present. They're kind of sandwiched between the main group elements. And they, though, are offset in their principal quantum number. Whatever row they're in, those principal quantum numbers for transition metals are 1 minus the n value of the surrounding main group elements. So this row right here would have an n value of 3. This row right here has an n value of 4, and n equals 5 for this row, and then the last row of the transition metals has an n equals 6. Then for the inner transition metals, you can see they are linked here. their principal quantum numbers are now offset by 2, whereas this top row of the inner transition metals has an n value of 4, and this one has an n value of 5. Okay, so those are the principal quantum numbers. The next type of quantum number to talk about is the angular momentum quantum number, and it's given a symbol L. I'll use a cursive L so it's very clear it is an L. So the value of L, the angular momentum quantum number, depends on n, and there are some possible rules for L, and the maximum value of an L can be 1 minus the accompanying n value. So let's go through these on the periodic table. So for this area and helium, this section of the main group elements, they all have the same L value, and that L value is 0. Then for the rest of the main group elements, right here, they all again have the same L value, which is 1. The transition metals all have the same L value, which is 2. And then the inner transition metals have an L value of 3. So let's kind of correlate the n principal quantum number and L values. So let's think about a principal quantum number of 4. Let's find everything on the periodic table that could have that principal quantum number. So for the main group elements, that's the row, 1, 2, 3, 4. So here, potassium, calcium, and the other main group elements in that row. For the transition metals, it's offset by 1. So this section, this row of the transition metals, would have an n value of 4. And then the inner transition metals, the very top row of those elements would also have an n value of 4. But these all have different L values. Here we have L of 0 for potassium and calcium. We have an L of 1 for the gallium, germanium, all the way to krypton. We have an L value of 2 for this section of the transition metals, and then an L value of 3 for the inner transition metals. So for each n value, there can be a few different possible L values. It just depends on which n value you're talking about. So I'm going to summarize these quantum numbers so far and then give a little analogy to them. So we have the principal quantum number. This is sometimes called the shell, and it tells us about the general energy of the electron. If we have some high n value, that electron is going to have a high energy. And again, we're only talking about ground state electrons. So in an analogy, if we were to think about the organization of a very complex building like a hospital, the principal quantum number would be analogous to maybe the floor or the story of that hospital building. So when we're making this comparison, the organization of electrons in an atom to the organization of a hospital building, the different levels indicate the amount of energy present and also the size. So the first principal quantum number, n equals 1, and then the first floor of our building will be the smallest and the lowest energy. Then the second floor will be a little bit bigger, have more energy, and so on and so forth. Then we have our angular momentum quantum number. and sometimes this is called a subshell. And in our analogy of a hospital building, this subshell would be akin to like a wing or a unit. So on one story, like the first story, the smallest, there might be just one thing, the emergency room. Then on the second floor, there might be a couple of things, maybe the radiology unit and the pediatrics. And on the third floor, there will be more units, etc. So this is telling us a little bit more in detail, a little more specific about the location of an electron in an atom or the location of something inside a hospital building. So those are two of the quantum numbers. Let's move on to the third that we're going to talk about, and that's magnetic quantum number. It's given the symbol M sub L. So just like L depended on the principal quantum number, the one before it, this one, M sub L, depends on the one that came before it, the L value. And to determine the M sub L value, we have a little formula that we use to determine the number of possible M sub L values, and that is 2L plus 1. And as you're going to see, the M sub L values start at 0 and then go in either direction from there. So let's talk about the M sub L values, and let's start with this area of the periodic table, including helium. We know that this area of the periodic table has an L value of 0. So we can do our little formula, 2 times the L value plus 1, and that gives us 1 possible M sub L value for all of these elements here outlined. The magnetic quantum numbers M sub L, they always start at 0, and if they can, go out from there. So the M sub L value for all of these elements is 0. Okay. Let's move on to the other section of the main group elements here. Everything not including helium. For here we know the L value for this section of the periodic table is 1. So we can do our little formula, 2 times the L value plus 1. That gives us 3. So there's 3 possible M sub L values. And those M sub L values include 0 and go in either direction from there. So we have a -1 and also a +1. Those are the 3 possible M sub L values for the elements in this green box here. So you can see there's 3 possible M sub L values, and there's 6 elements in a row here. So this series is now going to repeat twice. We're going to start at the negative, go through the positive, and then begin again. So -1, 0, +1, -1, 0, +1. So for an example, this element neon, it has one M sub L value, and that's +1. And so do all the elements below it in that same column on the periodic table. Okay, now this kind of pattern repeats itself for the transition metals. So for this area, the L value is 2. We do our little formula. 2 times the L value plus 1 gives us 5 possible M sub L values. They'll include 0 and go in either direction. We can do -1 and +1, then also -2 and +2. So these are the 5 possible M sub L values. And we'll go through this series twice. -2, -1, 0, +1, +2. Then -2, -1, 0, +1, +2. So these M sub L values apply to everything in a column. They would have the same M sub L values, different values for N, principal quantum number. Okay, so then the last area of the periodic table for our M sub L values is the inner transition metals here. So they have an L value of 3. We can do our little formula. 3 times 2 plus 1 is 7 possible M sub L values. We'll have 0, -1, +1, -2, +2, and now -3 and +3. So these are the 7 possible M sub L values, and we'll repeat this series twice. So -3, -2, -1, 0, +1, +2, +3, -3, -2, -1, 0, +1, +2, and +3. Okay, so that is the M sub L quantum number. Now, let's summarize what we've talked about so far. We have the principal quantum number, N. It's also sometimes called the shell. And in our analogy of a hospital building, this would be like the floor of that particular building. We also have the L, angular momentum quantum number. It's also sometimes called a subshell. And in our analogy, the L, angular momentum quantum number, is like maybe a wing or a unit. Then we just talked about the magnetic quantum number, M sub L. This is sometimes called an orbital. And this narrows down our location even further in an atom. So in our analogy of a hospital building, this would be like giving a room number. So that room number goes to a particular unit on a particular floor of the hospital. Then we have one more quantum number to talk about, and that is called the magnetic spin quantum number, M sub S. And this is narrowing it down even further. So in a hospital, most rooms would have 2 patients in them, and this magnetic spin quantum number would narrow it down to the patient, like bed 1 or bed 2 in that particular room. Okay, so let's go over the magnetic spin quantum number. For starters, there are only 2 possible values for M sub S for any element. That is either +1/2 or -1/2. So let's fill these in for the different areas of the periodic table. So for this area here, there's 2 columns, and each of them has a different M sub S value. So we start with the negative and go positive from there. So -1/2 for this column beginning with hydrogen, and then +1/2 for helium, beryllium, magnesium, etc. Then here, for the other part of the main group elements, we know the M sub L values. I'm going to write them out here. We have -1, 0, +1, and then it continues again, -1, 0, and +1. Now, this first section here would have M sub S values of -1/2, while the second part has values of +1/2. So you can see for each orbital, each M sub L value, -1, 0, +1, we get a 1 electron in them first, the -1/2 M sub S number, and then a second electron, the +1/2 number, is added second. The same theory goes for the transition metals. We have our M sub L values, -2, -1, 0, +1, +2, and again. And so the first part here, these elements would all have a -1/2 magnetic spin number, and the other part would have the +1/2. And lastly, for the inner transition metals, these right here, so I won't draw out the magnetic M sub L values, but the first half of them, 1, 2, 3, 4, 5, 6, 7, will have a M sub S value of -1/2, and then the other part will have the +1/2 M sub S value. Okay, so those are the 4 types of quantum numbers. Each electron in an atom can be assigned 4 different quantum numbers, the N, L, M sub L, and M sub S numbers. This gives each electron a unique set of quantum numbers. It's a little bit like giving an address to a person. Each person's address is unique. And again, what I've been talking about here is for uncharged atoms and their last electrons added there. So let's go over a couple of examples of how we use quantum numbers to determine an element, or how we determine quantum numbers for some element. So let's start with that. Let's say phosphorus. We want to determine its full set of quantum numbers. We'll start with the N value. So phosphorus, we can tell, is a main group element. So 1, 2, 3, it's in the third row. So its N value is 3. Then phosphorus is here on the right side of the periodic table. Everything there has an L value of 1. Then we have the M sub L values. So for this area, we have -1, 0, +1, -1, 0, +1. So phosphorus ends up being here with a +1 M sub L value, then M sub S. All of these first ones here will have a -1/2 M sub S, so that's what phosphorus has. So this is the complete set of quantum numbers for the last electron in phosphorus. So phosphorus has this atomic number 15, so that would be the 15th electron in phosphorus. Now let's go the other way. Let's start with a set of quantum numbers and identify the element that goes with them. So let's say you have an N of 5, L2, M sub L is +1, M sub S is +1/2. Okay, so first we have the N of 5. Let's find all the areas on the periodic table that have an N of 5, just for review. So for the main group elements, 1, 2, 3, 4, 5. Those 2, as well as the rest in that row for the main group elements. Then for the transition metals, where would they have an N of 5? It's just 1 offset, 1 lower. So this row of the transition metals has an N of 5. And then also the inner transition metals, this bottom row of those has an N value of 5. So just from that N value, we can narrow it down to just a few elements on the periodic table. Then we have an L value of 2. So we know that it has to be now in the transition metals, it has to come from this set of 10 here in this row. For M sub L, we can determine those values again. -2, -1, 0, +1, +2, -2, -1, 0, +1, +2. So there's going to be two elements that can have n of 5, L of 2, and M sub L of +1. And that would be here, W, the element tungsten, and AU, the element gold. So that narrows it down to two elements. Now we need to narrow it down to just one. And that is what we do with the M sub S value. So here, this first part will be -1/2. And the second part is +1/2. So with an M sub S of +1/2, there's only one option here, and that is the element AU, gold. So gold has the atomic number of 79, so the 79th electron in gold has this specific set of quantum numbers that would be unique, and all the other 78 electrons have a different set of quantum numbers. Okay, that is my lecture on quantum numbers. So thank you for watching, and I'll see you in class.